This is the first part of section 6.2. We're dealing with transforming random variables in this section. Okay, so this works a lot like we saw back in chapter 2 when we did transformations of data. You remember if we were looking at the distribution of all the test scores, and the teacher decided that he was going to add 5 points to everybody's score. What did that do to the mean of the distribution? What did that do to the spread or standard deviation maybe of that distribution? And then what if he decided to double everybody's score? What did that do to the mean of the new distribution? Like how the doubling of the scores changed the old mean to the new mean, right? And so what would it have any effect on the standard deviation? So we asked those kinds of questions about distributions of data. Here we're going to be applying the same rules. Actually, the same things apply when we're dealing with random variables. All right, so we're going to look at how to transform random variables, but we're going to be interested in what effects that these transformations have on the means and the standard deviations, and also the shapes and spreads of the histograms or the graphs of our random variable. All right. All right, so in 6.1, we learned that the mean and the standard deviation give us important information about the random variable. And then here again, like I just said, we're going to talk about how the mean and the standard deviation are affected by transforming the data. Now, it's not just the mean and standard deviation, but those are the ones we're going to concentrate on. We are interested in other measures of center and other measures of spread, but standard deviation and mean and standard deviation are those two measures of a location and center and spread that we use the most. All right, and then like I said already in chapter 2, we already, if you can remember, that when we added an A or maybe subtract an A, it added or subtracted that same value A to all the measures of center and location. So the mean, for example, but it did not affect the shape or any measures of spread. And then what happens when we multiplied by, say, a constant B? So it affected both the measures of center and the measures of spread. Remember that when we multiply measures of spread by B, technically B could be negative, so that's why we have this absolute value of B. Standard deviations, remember, are always positive, so it'll affect the spread. It'll multiply by the opposite of B if B is negative, because the absolute value is always positive. And then for both of these, they did not affect the shape of the distribution. So if the distribution is symmetrical, it'll stay symmetrical. If it's skewed to the left, it'll stay skewed to the left, that kind of thing. I guess with the one caveat is that if B happened to be negative, and it was skewed to the left, then now it's going to be skewed to the right, but it'll still be skewed. We honestly don't have negative B's that often. Okay. All right, so the example we're going to look at here is Pete and his Jeep tours. So Pete has a Jeep, and he gives sightseeing tours to people who show up at his shop. So he has a business, and he won't run the tour if only one person shows up. It's not worth his time and energy, and it's not worth the gas and everything else for his Jeep. So he will only run the tour if he has at least 2 people, and then he cannot accommodate more than 6. So himself included, he cannot take more than 6 people on his Jeep. And so this distribution of this random variable distribution looks like it gives us what? It gives us X, the random variable X, is the number of passengers on a randomly selected day. So if we look at the history of every day his business was open, we can see that 15% of those days, there was 2 people that showed up. On 25% of those days, 30 people showed up. 35% of the days, 4, and so on. So although he can accommodate 6 people don't show up that often, right? Only 5% of the time is there 6 people. Are there 6 people that show up? Okay, so this is the distribution, right? The probability distribution of this random variable x. All right, notice we also have a histogram drawn. And so the x values in this case are discrete, they're integers, right? So when they made the histogram, they centered them on the integers, which we often do. But just know that when we do that in our calculators, it doesn't do it that way. So it will not, in our calculators, when we create a histogram, it doesn't center it on the integers. Those numbers would be like the 2 would be on the left side of that bar. So I'm talking about here, like this 2 would be on the left side of the bar. This 3 would be on the left side of this bar, and so on. So just note, because we're going to make histograms in a minute, just realize that they're going to look slightly different on our calculators. All right, so we could calculate the mean and the standard deviation. We'll practice that in our calculators. Let's actually do that now. So in our calculators, if you'll take your calculator out, we want to put the random variable values, x sub I, we want to put those in list 1, and the probabilities are going to be in list 2. Also notice that all those probabilities add up to 1 or 100%. So put those into your calculators now. All right, so I'm assuming you've already put those in your calculators. If not, pause this video and put those in. All right, so the next thing we want to do is run a 1-var stat. So go to, hopefully you remember how to do this. You hit edit, go to calculate, and choose 1-var stat. So we want list 1 to be the list. List is list 1. Now we don't often use the frequency list, but in this case, our frequency list is list 2. So if you have the older 83 calculators or the older operating systems of 84s, you want to do that once the 1-var stat gets pasted back into your home screen, you want to then next type, input an L1, comma L2, and that will do the same thing here. And then we'll choose calculate. And that calculates a bunch of stuff here. And the ones we're interested in is this X bar. It calls it X bar. We refer to it as mu in this situation, but your calculator doesn't really know that we've got a random variable distribution, probability distribution. So it says X bar, but that's our mu. And then sigma, notice S is blank. In this situation, it just treats it as population data. So it's sigma sub X, and that's the 1.0, I guess 90, if you're going to round to 3 decimal places. Okay, so now let's practice how to create a histogram. All right, so we've done histograms, back in chapter 2, I think. Chapter 1, maybe, chapter 2. But let's do a histogram again. All right, so you're going to hit your second y equals to get to your plots. Go into plot number 1. Make sure plot 2 and 3 are off. Go to plot 1. Turn it on, and you want to choose the third graph. It kind of, looks like a histogram. And in this case, your X list, when we've done histograms in the past, we just have a list of so let's say we have the data for the last 365 days, right, that he has run his business. We might have, a bunch of 2s, a bunch of 3s, a bunch of 4s, right? And so in the past, we would list all the data, one data value for each day. So we would have 365 or whatever days he's been in business, pieces of data. We'd have to plug all those in. Well, the frequency list allows us to not put in all the 2s, 3s, 4s, 5s, and 6s, but instead say how frequent each one is. So it saves us having to type all that in. All right, so we have the X list is list 1, the frequency list, again, list 2. and then you hit graph. Now you might have to hit a zoom 9 to get your graph to show up, but when you do that, you're going to get this ugly graph like this. So the calculator will just take the data and try to fit it to proper classes, and usually it does a pretty awful job, or often it does. And so let's talk about now, because I don't think we've talked about this yet, how we can adjust the class width. So each of the bars in our histogram, if you look at the histogram up above, each of the bars has a width of 1, right? Because they all are integers and they all have 1 value. So the class width is 1. So the first bar is 2 up to, but not including 3. Now in this case, all of our values are integers, so it's just 2. But it would, if there were data that was 2.5, it would still be in that first bar. So it's 2 up to, but not including 3. If you right now with your calculator hit the trace button, you can see what class width it's using, and so we can see here that my little asterisk shows up here when I hit trace, and it's telling me what my class width is. So everything in this bar is from 2 up to, but not including 6. And it's 95% of our data. So that's everything. So it's taking these first 4 bars and lumping them together, and then this last bar is this last one here. So it's 5% here, there's 95% here. So that's not anything like we want. And so what we'll do to adjust the class width is we have to hit the window button. So top left corner on your calculator, hit the window button, and that gives you something like this that shows up. And so we've got to change these numbers, and these are appropriate numbers. These work pretty well. So we want the minimum to be 0. If you look up here, this is 0 here, so that's good, minimum of 0. And then the max is 7. Now you might say, well, wait, when we use 6, no, use 7, because 7 will make this point out here 7. So in our calculators, again, it takes these integer numbers and puts them to the left of the bar. So our calculator is going to call this value right here a 6. And so this will by default be a 7. So we definitely want a max of 7 to get our graph to look like this one up here. Okay. And then the X scale of 1, that is determining our class width. So definitely use a X scale of 1, and that in the histogram determines our class width, or how wide our bars are going to be. All right, and then, well, these other values work well, but sometimes you just have to play around with the Y's to make sure that the Y mins and Y maxes are fine. I think I have a Y max of 0.5, and the biggest of all of our bars is 0.35, so that should be fine. And I went a little bit negative, so that my x-axis kind of shows up and there's a little space below it. So my y min is negative 0.05 and my y max is 0.5. I just want to make sure that my value is big enough so that all these percentages will fit in there. Otherwise, the histogram kind of runs off the top of my screen. All right, and then once you've done that, hit graph again. Now don't hit zoom 9, because zoom 9 will tell the calculator, oh, do your best guess at fitting the data to the window. And so it'll take us right back to what we have here. So we can't use a zoom 9 if we make adjustments to the window. We can't do zoom 9, that won't work. It'll just take us right back to what we had. So we hit just graph at that point. Once you adjust your window, hit graph, and you should get something that looks like this. Okay, so now you can see that that graph looks a lot like the graph we had up above. All right, so let's start our transformation now of some data. So we have this random variable x, which again is the number of passengers that show up. And so now we're going to do some transformation. So how much does Pete charge these people or collect? So he collects $150 per person for this tour. And so this is like the revenue, right? How much money is he bringing in? So each of our random variable x values are getting multiplied by 150. So now we have a new random variable set here. Notice that the probabilities are still the same down here. So the probability that he makes that he brings in $600 in revenue one day is the same as the probability that he has 4 people, right? I mean, because we've just taken those x values and multiplied by 150. So now let's talk about what happens to the mean and to the standard deviation of the original x values. So as you can see, we know what the mean of x is, and we know what the standard deviation of x is. Now let's see what is the mean and standard deviation of this new random variable that we're calling c. All right, so you can see, if we graph the data, of course, the scales are different, right? So if we look at the graph, the scales are different in the y-axis. Oh, actually, no, those are percentages. Those are the same. But the scale here in the x-axis is different. Instead of being 2 through 6, it's now 300 through 900. So the scale is different, but you can see that the shape of the distribution is the same. All right, so now let's look at the mean. So the mean, how can we calculate the mean for this new random variable x? Well, we can always just take each value of c and multiply it by its probability, and that's what I'm doing here. If you went through all that trouble, you would get this same value, 562.5, which is really the same as taking the mean, 3.75, and multiplying it by 150. So we can just simply take the mean of the random variable x and multiply it by multiplying by our transformed value of $150 per person. And then standard deviation. Remember, for standard deviation, we're going to take each value of x, or I'm sorry, of c, and subtract the mean. We square it, we multiply it by its probability, and we do that for each of the values, add them all up, and then take the square root of them. We could do all that, but we would get the same value as the original standard deviation multiplied by 150. All right, and so we get 136.5. All right, so remember, the standard deviation and the mean are both affected by multiplying. Both the mean and the standard deviation would just get multiplied by 150. All right, so kind of verifying here, sort of some rules, right? So when we multiply by b, we simply are going to multiply the centers by b. So in other words, the means is what we're sort of interested in. So when we multiply by a value b, we multiply the measures of center also by b. All right, and when we multiply or divide by b, we'll multiply or divide the measures of spread also by b. And in actuality, it's the absolute value of b in case b happens to be negative, just like we saw when we dealt with data. All right, and the shape does not change. We saw that. The scale and everything will change, but the general shape, it looks fairly symmetrical, and it still is fairly symmetrical. All right, so now let's talk, that last slide was dealing with multiplying. Now let's talk about adding. All right, so we now know how much revenue. This is the distribution of the revenue that he'd be bringing in, right? The random variable probability distribution for the revenue or the money he collects. And we have here the mean. Again, we've listed the mean and the standard deviation that we calculated on the last slide. So now let's talk about adding. In actuality, we're going to subtract. We're going to think about, okay, so how much does it cost him, Pete, to run his tours? So it costs him $100, regardless of how many people are in his Jeep. He's got to pay for gas, he's got to pay for permits, he's got to pay for ferry pass or whatever, right? So he's got a fixed cost per trip of $100. And so what we really want to do is we want to subtract $100 from the random variable C to find now our random variable V. And so that's what we'll use for V is the profit that he makes. And so we want to now think about the, well, what will the shape be? And what will the mean of V be and the standard deviation of V? So how does subtracting $100 from each of the values of the random variable C, how does that affect the mean and the standard deviation of the random variable V as in Victor? Okay, so we could go through the whole process again of taking each value of V and multiplying it by its probability, like we're doing here, add them all up, and that would give us our standard deviation. Another way of looking at that is sort of our a weighted average, right? But that's our expected value of V, and the expected value of V will just be the same as the expected value of C, but subtracting $100. So subtracting that 100 affects the mean. So the original mean of C, we're going to subtract 100, we get the mean of V. And then the standard deviation, we could do that as well. We're going to see, though, that that does not change. So the standard deviation of V is equal to the standard deviation of C. If we went through the trouble of doing all this work, we would see we would still have $136.50. Okay. And then the shape of this thing, again, still the same. We still have the same general shape. Still fairly symmetrical. Okay, the scale, of course, is changing down below, but the spread does not change. The shape certainly does not. All right, so just to kind of verify our final rule here is if we add A, right? So if we add A to add the same number A to each of our random variable values, then it adds A to the measures of mean, right? Measures of center, or in this case, we're going to be more concentrating on mean. It does not affect the measures of spread and does not affect the shape of the distribution. And again, that was exactly what we saw in chapter 2 when we did a similar thing with distributions of data. All right, so if y is the new random variable, and if y is the new random variable, and we're doing a transformation, so we're taking all the values of the random variable x, multiplying by b, also adding a, so we can do both at the same time. What happens to this what happens to the measures of center and spread for our random variable x? How do those change for your random variable y? So the probability distribution of y has the same shape as the probability distribution of x. That doesn't change. What happens? How do we calculate the mean or the expected value of the new random variable y after we've done this transformation? All right, so the mean is affected by both adding and multiplying. So we multiply and add A and B to the original mean of X to find the mean of Y. Okay, and the standard deviation, well, that doesn't get affected by adding A, just by multiplying by B. And so if you remember, it has to be the absolute value of B, because B could be a negative number. Okay, so linear transformations have similar effects on other measures of center, so the median, the quartiles, that kind of thing, and the measures of spread, which would be the range or interquartile range. All right, it doesn't matter whether we're dealing with sets of data like we did back in chapter 2, or whether we're dealing in this chapter with random variables, the effects are the same. Okay, and one more thing. So the example we did with Pete's Jeep tours, that is just X. So the random variable X, the random variable C, the random variable V, those were all discrete random variables. But these rules that we've established for transformations of random variables are true, and the same rules apply regardless of whether the random variable is discrete or whether it is continuous. All right, so whether we're dealing with a normal curve where we have a continuous random variable under a density curve, for example, the rules will be the same. How do we transform the mean? How do we transform the standard deviation? It will be done the same way, regardless of whether the random variable is discrete or whether it is continuous. All right, so let's look at an example. A report by the National Center of Health Statistics says that the height of randomly chosen 20-year-old man is a random variable, and the random variable they're using is h, with a mean of 5.8 feet and a standard deviation of 0.24 feet. So find the mean and the standard deviation of the height, and now we're calling a new random variable j, of the randomly selected 20-year-old man, but let's convert it to inches rather than feet. All right, so remember that what would I do to the h? I'm going to multiply by 12, right? If I'm going to transform, I'm just doing dimensional analysis essentially, right? You're taking feet and converting it to inches. H, the random variable h, was in feet. So I take each possible value of the random variable h, multiply by 12, and that will give me my random variable j. Now, of course, this is continuous, right? This is a normal curve. It's a continuous random variable. So we can't take the individual values and multiply them because there's infinitely many random variables. But we can apply the same rules we just learned to h in order to get to the mean and standard deviation of j, even though this is a continuous random variable. All right, so the mean for j, we're not adding anything. In this case, we're converting from feet to inches, so we're multiplying by 12. So the mean, the new mean, is going to be the old mean, 5.8 times 12. And then what do we do to get the new standard deviation? It was 0.24 feet. We're going to multiply it by 12 as well. So now we have this new mean and standard deviation. We did a transformation by multiplying by 12. All right, so now let's ask this question, now that we have things in inches. A modeling agency is looking for a 20-year-old man that is shorter than 64 inches. If they randomly select a 24-year-old man from the population, what is the probability that he is indeed shorter than 64 inches? All right, so we're looking at the mean. We know the mean, we know the standard deviation. We're going to use 3 steps here. So when we're calculating, I know before we were using 4 steps, but when we are trying to calculate a probability, we'll go back and sort of use a 3-step process. All right. So let's go through this together. All right. So we want to do 3 steps here, and so the first step is going to have 3 components to it. So part 1 of step 1 is to define the random variable. So we say something like the height of a randomly selected 20-year-old man is a random variable j, or j is a random variable representing the height of a randomly selected 20-year-old man, something like that. So define the random variable. What is it that j represents? All right, so that should be kind of in a sentence form. All right, the second thing is we want to talk about what is the distribution of j. J, we know, has a normal distribution, and what is that normal distribution? So j has a normal distribution, and we say, we define that that normal distribution by the mean and by its standard deviation. All right, and then the third thing is, well, what is it that we want to find? So say the probability that we're looking for. All right, so we want to find the probability that j is less than 64 inches tall. Okay, so that's step one. Step one involves three things when we're dealing with probabilities. I know we've done with four steps in the past, but now we sort of, when we are looking for a probability calculation using multiple steps, we want to use three steps. So just step one, step two, step three. First step has three components. Make sure you have those three components. The next step two, is sort of the do, if you will. It's the calculation part. All right, so we're going to calculate. This is a normal distribution. You should have a normal curve drawn with labeling of the mean in the middle and value of interest, in our case 64, with shading, appropriate shading. So something like this, right? So we have our mean 69.6 in the middle. Our value of interest is 64. Make sure that's on the left side. Again, I've got mine sort of to scale. I used some software to create mine, but it doesn't matter. Your 64 doesn't have to be that far into the tail, so long as it's on the left side and that you're shading to the left of that. Okay. All right, so we definitely want a normal curve. You will lose a point in my class, and you could potentially lose points on the exam, AP exam in May, if you don't have a normal curve drawn with shading. All right, so if you're going to use technology, we saw one of these the other day. You're going to, on your calculator, press second vars, which is distribution. And I'm trying to get my calculator on here. So second vars, which is distributions, and then go down to your normal CDF. Now, the values in green, you're not typing those in, right? But on your paper, you have to say lower, upper, mean, standard deviation. So I know that you understand what those values are, as opposed to just numbers you're plugging in. All right, so the lowest value, there is no like low value, because on the normal curve goes on forever to the left, right? So we just want to pick a substantially low number, -1,000, -10,000, something substantially low. I mean, even if you said -100, that would be far enough down into that tail that the area to the left of that value is so minuscule that it doesn't really matter. So often we'll use -10,000, -1,000, something like that. All right, the upper bound is 64, the mean 69.6, and the standard deviation of 2.88. So that will just simply give us the shaded region. Remember, that shaded region represents the proportion of men that are shorter than 64 inches tall. And so that's what we're thinking about, right? And in the whole population, 2.6% of the population of 20-year-old men are shorter than 64 inches. So if we randomly pick one of these men from the population, we have about 3% or 2.6% chance that they would be shorter than 64 inches. So not very likely, right? Pretty small probability that you would do that. Now, I'm also showing you here how you would do this with your z-score table. You know, you would first calculate your z-score, and that's -1.944, and then you would pick up your z-score table and look for this value. Well, we would really have to look for -1.94. Remember, 1.9 is on the left of the negative side, and then the 0.04 is up at the top, and then this would give you this value. Now notice our answers are slightly different because the z-score table's accuracy only goes out to 2 decimal places. Here, this 4, for example, isn't being used in the z-score table. So this value of 2.62% is a little low, a little high compared to the more accurate value over here. All right, and then the last step is the conclusion. So you want to, in a sentence, answer the question. So answer the question that we posed up here. What is the probability that he is shorter than 64 inches? All right, so the probability of a randomly selected 20-year-old man that probability of randomly selecting a 20-year-old man who is shorter than 64 inches is about 2.6%. All right, so this is the 3 steps. This is a good model of what you should be doing when you're asked to do a 3-step process. It may not always be a normal curve or even a continuous random variable, but you want to follow these 3 steps. And again, this is a pretty good model. All right, so this is your homework. You probably guessed what the asterisk means here on 45. That means that number 45 is a 3-step problem. Make sure that you're doing that as a 3-stepper.